between two atoms. So bond, electrons between two atoms. So this means when you go through and define or analyze an IR spectrum, you should be providing two atoms in your answer. What if you provide more than two atoms? You're not looking at a bond. You're looking at multiple bonds, which at this stage in the game, you're now doing wrong. IR is a bond, and only a bond. Okay? Because we're causing a bond to vibrate. Okay? There are other types of vibrations that involve other bonds. Okay? Those are still IR active, and we could still analyze those in the IR. However, most of those types of vibrations happen in a range where thousands of other things happen, which means you see a peak, and that peak could correspond to 20 or 30 different structural features. For you to analyze that, it's a bit silly, because you're now saying, well, it's not 1,000 possible options, it's only 20 possible options. In a multiple choice test of 5 answers, or even 4 answers, 20 possible options didn't really narrow the field. Okay? So avoid overanalyzing the IR. When you see other types of bond stretches, bends, or frequencies where they're listing more atoms, those are still IR vibrations. They're just vibrations you're not responsible for, okay? Because you don't want to be held responsible for them. Okay? We also talked about our stretching frequencies. The one in red is going to be your important one. Okay? Your wave number, and these are supposed to be stretching frequencies, which is technically your wave number. What we're trying to say is our wave number. Our wave number will increase with increasing bond energy. Okay? Conversely, what if the bond gets weaker? Well, wave number decreases. How could a bond become weaker or stronger? It could become stronger by increasing from double to triple bonds. How could it become weaker? Triple to double or single. So let's take a look at a couple real quick examples here. No. Don't even open that can of worms. I want to know the relative energy of the carbon-oxygen double bond. Okay. When I say the same, so they show up at the same wave numbers. Do these two show up at the same wave numbers? No, why not? Okay. So nitrogen being more electronegative than carbon, you're saying there's an inductive effect pulling electrons away. Careful on that. Okay. If you tried to pull those pi electrons out towards the nitrogen, what happens? You exceed the octet on the nitrogen. Okay. What should you be thinking about instead of an inductive effect? Not electronegativity, it's the next one. Resonance. What happens with resonance? And we have a resonance structure that shows what kind of bond between the carbon and the oxygen. A single bond, which means when I look at the stretching frequency for that carbon-oxygen bond, is it weaker or stronger than a standard double bond? It is weaker, which means the stretching frequency for the carbon-oxygen in an amide functional group is lower than that for a standard carbonyl. How much lower? I don't care. It's lower. Okay? Don't get into quantifying with the IR. Look at your relative relationships. Okay? Questions on that? Okay. This is the next kind of fun one to realize when we're looking at our IR. What IR is detecting is bond dipoles. This is why when we look at, say, a carbon-oxygen double bond, we get a really strong, intense signal. Okay? Or when we look at the OH bond. We get a really strong, intense signal because those bonds are very, very polar. But what happens to, say, carbon-carbon single bonds? You're told not even to analyze them. Why not? Nonpolar. The carbon-carbon bond is so nonpolar that it doesn't generate a dipole. What does that mean happens to the IR's ability to see that bond? It goes down, which means the intensity of the signal goes down. So in this previous slide, we're looking at our left-right. Where does our signal show up? In this slide, we're now looking at how intense the signal is. Okay? Just because a bond is present in a molecule doesn't mean that we can see it. We know theoretically where it should show up according to our wave numbers and the energy of the bond, but that doesn't mean the signal is intense enough for us to be able to detect it. And this comes back to our dipoles. Okay? The biggest thing the IR is looking at is how that vibration changes your electric fields and all sorts of other weird nonsense if you want to look at it. Okay? What happens if your molecule, say, let's look at an example here, had a triple bond in it, say a carbon-nitrogen triple bond? Would we expect to see a triple bond show up in the IR? Triple bonds should show up in the IR. Okay. Does that triple bond have a dipole? Yes, nitrogen is much more electronegative than carbon. I do expect to see a signal for that particular type of bond. What happens if I now move to a carbon-carbon triple bond? Number one, is that going to change the energies? Yes. So where it should show up is now going to vary from our nitrogen. Okay. Next aspect on this, should I see the carbon-carbon triple bond? Okay. With the carbon-nitrogen triple bond, we can immediately jump to it having a dipole right out of the gate, okay, because nitrogen's more electronegative than carbon. As an added bonus, how many bonds can a nitrogen have? Three. How many bonds can carbon have? So by looking at the triple bond between two carbons, am I looking at a complete picture? No. So let's complete that picture out. Would I expect to see the carbon-carbon triple bond? Okay. Or said another way, what if I had, instead of drawing it with the hydrogen, I instead drew it like this? In our leftmost case of the blue one, is there a dipole? Our spring is in here. We're now looking at two masses, the mass out here and the mass out here. Are those masses different? Yes. Is there a dipole? Yes. That triple bond is now visible in the IR because of that dipole. We look at our red example. We still have the triple bond, so it should have some vibrational energy within the IR. But we look at the left side of the mass and the right side mass. Is there a difference? No. What happens to the signal for our triple bond? It becomes exceedingly weak so that we cannot end up seeing it. Okay. What if I go through and add a stupid eraser? Make it a CH2CH3. Okay. Now I should expect to see it because there are differences on opposite sides. How much is that difference? Not, excuse me, not a whole lot. So while we may be able to detect this signal, it's not going to be as intense as, say, the carbon-nitrogen triple bond. Okay? So when we're looking at IR, we have to be a little bit careful. Okay? Most of our bonds have dipole moments, which means they are IR active. There are a few cases that they have zero dipole moment, in which case they are IR inactive. The classic example is symmetric triple bonds, okay, which was our first, well, almost our red case. Okay, So just kind of watch out for that. It's kind of a little zinger some people like to test on. I don't think I've ever tested on it. Okay? But it's one of the complications within our IR. Major regions of your IR spectrum. So we've got our intensity of our signal, the percent transmittance. 100% transmittance means what? No interaction between light and the molecule. The light passed perfectly through the sample. Okay? A 50% transmission, that's 40%, means some of the light went into the molecule. It was absorbed by the molecule to do cause our bonds to vibrate. Okay? That's why we're seeing this now signal show up. Okay? Where does it show up now? Well, that corresponds to our wave numbers at the bottom, which gives us some more information about our signal. Unlike UV vis, our wave numbers directly correspond to energy. The larger the wave number, the larger the energy. Okay? Within that, we can now break it down. Our full range, usually 4,000 down to about 500. Okay? Within this slide that we've gone through and kind of identified particular ranges that can be useful. The thing that's not showing up on here is what, and this always irritated me at ASU. One of the instructors would go through and put this big massive red X through this section. Because that section of the IR spectrum is known as the fingerprint. Okay. When you go up and talk to your friends, do you insist on fingerprinting them first to ensure that they are who they say they are? Okay. Probably not. There's other easier ways to determine that. Okay. So we don't look at the fingerprint region very often. Is there still useful information there? Yeah. Okay. So the fingerprint region is not something you should cross out because there is stuff there. You should just realize that you shouldn't be looking into the fingerprint region unless you are forced to. How do you know you are forced to look in the fingerprint region? I tell you to look at the fingerprint region. That's pretty much it. Okay? Other than that, don't worry about it. Everything higher than that, you should theoretically then be able to analyze. I kind of stretch this fingerprint region a little bit further. I actually take it all the way out to 1600. Okay. And I am now very, very hesitant to analyze anything less than 1600. Is there useful information there? Yes, but the odds I analyze it correctly start to dramatically drop. That 16 to 1400 range, I'm still maybe 70% of the time correct. As soon as I hit 1400 and under, I'm probably at 50% correct. Okay, that's a pretty horrible average, so I don't even bother to look at the fingerprint. That 16 to 1400, I have some odds of getting some information out of, so I'll start to look at it, but for the most part, I leave that alone. Which then means I'm only looking at 1600 and greater. So if we look at this breakdown, we get some kind of bond to our hydrogen stretches showing up. We get triple bond signals, and we get double bond signals. That's it. Okay. Other bonds do show up, and they can drift into the fingerprint range, and sometimes they can drift out into our normal standard range. Okay. So don't overanalyze. The idea is to get through a quick analysis as quickly as possible. Okay. I always love to show this slide because there's some instructors that insist on passing this out as the things for IR. Okay. Then, oh, you need to solve IR? Here, take this chart. Okay. And if you look at this, this does give you useful information. Here's our 400. Here's our 4,000. If we have an alkane, we see some signals. Here's our little black lines representing where we would see those signals. And those would correspond to a tertiary butyl, an isopropyl, an N-propyl, an ethyl. Okay. Really, we're saying all of our alkanes show signals where? 3,000. Around 3,000. So why don't we just say alkanes at 3,000 and leave it alone? Okay? Which is what I do. Okay? This information is more correct or more accurate, okay? But it's what level of accuracy do you need within this? You don't need this detail. Believe it or not, this is probably a page of hundreds. Okay? If our library had the background for this, you would find a book full of pages just like this, saying this is what happens when you have this functional group. Here are all the possible signals that show up. Okay? And some people are expected to be able to interpret these. You are not. What you are expected to be able to interpret, not quite yet, would be these. Okay? The OH bond shows up between 3,300 and 3,500. Why is it a range? Depends on what it's attached to. If I attach that oxygen to a carbon, is that going to change how that bond vibrates? If I attach that oxygen to a nitrogen, does that change it? Yeah. Those changes are going to cause where the signal shows up to change. Sometimes outside of that range. Okay? These ranges are kind of your 95% confidence. They're probably more like 90% confidence. Okay? So we can slide outside of these ranges. So don't use them as the Bible, but use them as a rough guideline. The next part is if you just see those, we don't really know what the signal looks like. Okay? So I've also included what the individual signal looks like, some idea of it. Okay? So what does intense mean?
Very far down.
Okay? We get a very low percent transmittance. Okay? Well, what is very low? Okay? Until you look at some spectra, that's kind of a random statement to make. And it is a perfectly random statement to make. Okay? You need experience looking at individual spectra. If you go through and look at the packet that I've posted online, I give you representative signals. Your textbook will do something similar, except they make you look at the whole spectrum as opposed to just pieces. Okay? So to analyze IR correctly, you need to have an idea of what each of those things looks like, so that when you see a spectrum, you go, ah, that looks like that. Okay? This one was intense and broad, and the nitrogen is medium and broad. Oh, that's useful. Okay? But that's the description. That's your standard description. And if we look at the ranges, they're almost identical. Okay? So how do you distinguish between them? Practice by looking at the IR spectrum. Okay? The next two that are really, really important, okay, and the textbooks, I'm not positive how our textbook does it, but most textbooks don't get into this. Your CH stretches. What happens if you change the hybridization of the carbon? It's going to change the bond because we have different hybrid orbitals being involved in the bond, different p character, which then means the bond length changes, which then means the spring changes and everything else changes. How much does it change? Changes pretty much on a dime at 3,000. If you have a CH atom in your, or bond in your structure where the carbon is sp2 hybridized, you will see a signal just barely greater than 3,000. You see a signal at 3,005. What does that mean? CHSP2. Okay. Not perfect, but pretty darn close to that. CH, where the carbon is sp3 hybridized, 2,995. CHSP3. Okay. Will it slide a little bit lower, a little bit higher? Yes. Okay. So when we look at these, you see varying intensities and you tend to see groupings of peaks. Okay. So it's not just a single peak, there's a bunch of peaks kind of generally around it. Again, how do you know that? Experience by looking at the IR or looking at the examples given to you in that worksheet. Okay. Carbon triple bond, okay, can be weak. It is typically very sharp and it is very, very lonely. When you look at the IR spectrum, there's a dead range from roughly 2,100 up to 2,700. Nothing shows up in there except the triple bond. Okay. So if you see this weird peaks floating out in the middle of nowhere, it's probably because there's a triple bond there. Okay. Realize to see the triple bond, our molecule must be unsymmetric. Okay. Last big one, the carbon-oxygen double bond, 1700. Usually very, very intense, more intense than any of the other signals, including the OH. And sharp, you love that-ish. Okay. Again, depending on the characteristics, it may be very sharp or it may be kind of broad. Or, yeah, not broad like an OH, but broader. Okay.
So when you see a triple bond, you should know that you're not going to have a symmetric.
You're not going to have a symmetric molecule. Good point. So if you see a triple bond, immediately your molecule is not symmetric. So if we go back up to this thing, if we look at our signals, this is kind of a nice spectrum because we've got this grid pattern that can allow us to see it. Our 3000 mark is this line. And if we look at all those peaks, where are those peaks showing up? Less than 3000, which means that grouping of peaks are cH-sp3. Right. A couple people have already come to me and asked about IR, and they show me this. People that did that, how did I respond? Okay. What the hell is sp3? sp3 is a hybridization of, at best, an atom. IR doesn't show you atoms. What does it show you? Bonds. So writing sp3, I'm not going to give you any credit. Okay? You need to tell me CH. If you give me just CH without the sp3, you'll probably get partial credit, but you should be able to give me more information. That more information is that that carbon is sp3 hybridized. You should be providing both those pieces of information.
If just one of the peaks was over 3000, would that mean that there's also an sp2?
Yep.
Okay, just making sure.
So CH-sp3s, how often are we going to see those in our compounds? A lot. Virtually all of our compounds have CH-sp3s. Okay? IR just tells you if that bond is present. It doesn't tell you anything about how many. So if our structure happened to have a carbon-carbon double bond with a hydrogen off of one of those, we would also expect to see a signal show up over there. Just greater than 3000. We would see both. What happens if signals overlap?
You can't really see it.
It makes it a mess to analyze. Okay? Are you still responsible for it? Yep. Okay? So you have to process that accordingly. You'll notice within the rest of this spectrum, we've got a bunch of other signals popping up, and nice of the textbook to go through and do this, they labeled what those things meant. Okay? Why might I flip out at some of those labelings, and in fact, all of those labelings? Touche. What else? There's more than one bond. Okay? All of those have at least 3 atoms. There's more than one bond. Okay? Which makes them a lot more difficult to analyze. Can you do it? Yes, the textbook clearly did. Okay? What else is the issue with labeling those? That range is all the fingerprint range. You shouldn't be touching that unless you are forced to do it. Okay? Which brings up the next issue. That last one, that's outside of the fingerprint range. You are technically responsible for it. What are the odds you're going to be able to figure out what that signal is? Very, very unlikely, which means you should have left it alone, which is what I was telling you to do, because it's between 1600 and 1400. Dangerous range to play with. A lot of things can still show up there. Not worth the trouble. Okay? So your analysis needs to be sitting on those, what is that, 6 signals. Absolutely need to have those memorized. If you don't have those memorized, you will do horribly when it comes to IR. Okay? The next part of this is, I would say, let's take this to the next level. What if you've got that down, you want to now apply a little bit more? Okay? These can also be more useful or more helpful. Okay? They can give you some more structural information. You'll notice I'm repeating a lot of information. The OH I had on the previous slide. But on the previous section, what did it say the OH showed up as? 33 to 35. And yet somehow here, the OH shows up at 27 to 32. Why is it all of a sudden changing? when near a carbon-oxygen double bond. How would that affect the OH bond? What functional group do I have? A carboxylic acid. How attached is the hydrogen to the structure if it's an acid? It's not, which means that bond has become weaker, which means the frequency at which that signal shows up goes lower. That's why it shifts. Okay. Do not reference a big, large signal, right, 2700 or 3200, as a carboxylic acid. I will lose my crap on that one. Because you reference it as a carboxylic acid, how many bonds are present? Okay, more than one. 1, 2, 3 at least. Okay. What is showing up in that range? Only the OH. That is the only thing showing up there. Because it is close to other bonds, some other things stack. Okay. The NH, you'll notice on the previous slide, just general information. Shows up in that range, medium, not as broad. What have I added here? 2 peaks, 1 peak. Oh, that's nice. Let's fix that real quickly. That should say secondary. As I start to write primary again. What does primary and secondary refer to? As a hint, this one is primary. This one is secondary. How many hydrogens are on the top one? 2. What does primary mean? Primary?
2. 1 bond.
Primary really just means 1, right? Okay. So 2 hydrogens, so that's not quite right. It's actually referencing those atoms being carbons. A primary amine means that our nitrogen has 1 carbon connected to it. A secondary amine has 2 carbons connected to it. What kind of signal would I expect to see for the NH on a tertiary amine?
There's no NH bonds.
On a tertiary amine, how many carbons are attached? How many hydrogens are now attached to the nitrogen? 0. Should I expect to see an NH? No, because there isn't one. Okay? Yeah, that was a nasty trick question. Didn't you like that? Okay. CH, where your carbon is sp hybridized, this would be looking at a triple bond at the end of the structure. Happens so rarely that I typically don't bother to memorize it. That shifts up to about 3300. Same range as our OH and our NH, but comes much, much sharper. Okay. In fact, it's very sharp. CH, again, 28 and 2700. I've already listed that kind of range for a CH before. What's different about it now? It's near a carbon-oxygen double bond. Okay? Because it's near that other bond structure, that's changing where it shows up. Why might we reference that one? If we look at that, we have a CH near a C double bond O. What do we have? An aldehyde. Remember those functional groups you should know how to name? Okay. One of the big things that we can get out of IR spectroscopy is an idea of what functional groups we have present by looking at the bonds. An aldehyde is a functional group. You should be able to identify your aldehydes. Okay. Carbon-carbon double bond. 1650, typically where it shows up. Okay. That's right outside the range where I said you should be able to do, so you theoretically should be able to nail that down. You will typically see me not reference the carbon-carbon double bond when I analyze IR because chances aren't as good. Okay? That 1650, I'm probably correct 85% of the time. not worth my risking it. Okay? The other one, 1600 and 1450. You'll notice that's an entirely different frequency. Why is that changing? That's because the carbon-carbon double bond is coming about when I have an aromatic compound. Okay? Said another way, I have a benzene ring with carbon-carbon double bonds. Why are those carbon-carbon double bonds not showing up at 1650, but instead at 1600 and 1450? Because of resonance. The bonds have become individually weaker because they're all being shared around the structure, which means our signal from 1650 drops to 1600. What's this 1450 floater? That ring can actually bend. You're looking at the ring bending. That's what that frequency is. Again, multiple atoms. The last one, C single bond O, well into the fingerprint region, but it tends to show up as a fairly intense, relatively broad signal, very similar to your carbon-oxygen double bond. Okay? So sometimes I'll analyze, look for that. Okay? Again, dangerous peak to identify. Okay? But if you have some more information, you can say, oh, yeah, it is there. So if we finish an analysis and we know that we have an alcohol, what does an alcohol look like? And I should expect to see an OH, and I should expect to see a CO. So if I think I have an alcohol, I'll go back and look for that CO. If it's not there, my analysis is probably wrong. Okay? Questions on these memory things? Okay. 10 seconds. Analyze. As I walk through all your viewpoints. And that was enough. Next one. 10 seconds. Fair enough. So I'll reset the clock, but you should still be able to figure it out even without the wave numbers down there. Ten more. Whoops. 10 more. They're digital spectra. They mess with us. So let's go all the way back to the first one. In our analysis, so it can be helpful. You'll notice that, yeah, the scale is difficult to see. This comes from, these are fairly standard spectra. When it comes to your exam, I do try and make that scale a little bit more obvious. If it comes down to it and you can't see it on the exam, let me know. Okay? And then I will go and I will draw it bigger. Okay? So when we look at this, we're starting at 500, 1,000, 15, 2,000, 3,000, 4,000. So yes, our scale changes as we move through it. Okay. When we go through to identify, some signals we should nail down, those two. Okay. The one on the right, if that's my 1,500, 16, 17, I'm at 1,700, that gives me a carbon-oxygen double bond, and I move on. The next part is deciding that 3,000 line. So I'm in the CH range for those, so now the question is, are they CH SP2 or SP3? And it's not the easiest to see. And you may have a hard time nailing that down. So this is what you can do, is tear apart your exam and look at some pretty pictures that somebody drew on this board. Is line it up with that bottom line. Take your second piece of paper, drop it at 3,000. Where's those signals? Less than 3,000. Okay? So use your exam as an advantage. I have no idea what that is. Use your exam to your advantage to figure out where those lines are, because that line is relatively sharp. So we have cHsp3. Anybody analyze anything else in this?
Would you look at the peaks on the left side as alkenes?
The left that I've got labeled as blue?
Yes.
So alkene I'm going to have a problem with, because as soon as you say alkene, the first thing that pops to mind is this, in which case, no, you're wrong. Okay? What you're actually referencing is an alkene with a hydrogen on it. Okay? So I was wrong in saying you were wrong to begin with, because you do have a hydrogen on an alkene structure. Okay? Sometimes. Okay? But in both cases, we need to be more specific. An alkene applies to more than one bond. So which bond are you referring to? The CH bond. So you're saying a CH that is sp2 hybridized. Those need to show up just greater than 3,000. That sequence of peaks shows up at 33, 34, 35. That's a little bit too high. Okay? So not CHsp2. Anybody else want to throw down a guess on that? So you could try a CHsp. CHsP's super pinpoint sharp. That's pretty broad.
Whenever you have a C double bond, oh, it always has that shape right there.
We'll get to that. Okay, so that's too broad to be a CHsP. What else could show up there? The NH. The NH is the only one that could potentially give you multiple peaks there, but that's giving you 3 peaks, and it's not really intense enough. Okay, so the NH I would at least accept as, okay, that looks reasonable. Okay, but it still looks odd. It's fine to write on your IR that you don't trust the information you're writing down. Okay, acknowledge that, because if you later go back and check, and you don't put the question mark, you go, oh, I don't know why I said that, but I wrote it confidently, so I must be right. Okay, acknowledge that you don't know what it is. Unfortunately, this peak is a sneaky, sneaky, sneaky peak. Okay? It is not an NH. It is actually a carbon-oxygen double bond. Where does the carbon-oxygen double bond show up? At 1700. It is so intense that it absorbs the energy twice. Meaning, it doubles our energy, and so we see a doubling of this peak. What is doubling of 1700? 3400, which is right about where that peak showed up. It is known as the carbon-oxygen double bond overtone. Okay? It's a doubling of that super intense signal. Anytime, or not anytime, but most times you have a carbon-oxygen double bond, you will see that doubling effect. And you get that weird kind of camel hump shape thing back there. Okay? Next one. OH. CH, how'd you get SP3? You're right next to the screen, so that helps.
It's closer for it's on the other side. It's less than 3,000.
Just under 3,000. Rest of the signals, there's my 1500 line. Yeah, I don't know. Doesn't look like a carbon-oxygen double bond. If it was a CH double bond, I would first expect a signal at 1650. I don't see that. Well, maybe aromatic. If I have aromatic, I should expect CH sp2, which I don't have. Okay? So I don't have an easy way to analyze that, so what do I do? I leave it alone. I identified an OH, so I might get a little bit ballsy. Say maybe that's the CO. Okay? Is it right? I don't know. Put a question mark. If you have an OH, what are the odds you have the CO? Pretty good. Okay. And the little blip here, where it's showing up at 1700, you might start to think carbonyl. But remember, carbonyls are super intense. So that's not your carbonyl. So it's just a weird artifact of the spectrum. Next one. So, and here again, may not be easy to see. This is where that board comes in handy because I probably can't draw a straight line. We have a peak bigger than 3000, cHSP2, and we have peaks under cHSP3. If I have a cHSP2, what does that likely mean is somewhere else in my structure? A carbon-carbon double bond, which shows up 1650. Okay. Here's my 1600 line. My peak is almost at 1600, so it's not quite 1650. So it's probably not just a standard alkene. It's possible. There's our good answer. It could possibly be the carbon-carbon double bond of an aromatic. If it was aromatic, what else would I expect to see? Peak at 1475. So this could very likely be a ring with some cHSP3s somewhere in the structure. Okay. And the last one. Should get some cHSP3s. What was that? Yeah, that's going to be a hard line, and I'm not sure I can. Of course, the screen likes to move. It's hard to get that flat. It's really, 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 really close. Right. Sitting almost perfectly on that line. So what would you do? I put a question. Okay. For sure we have the cHSP3. That one was definitely under the cHSP2, kind of questionable. That peak? C double bond O. I like how you all shouted that out, or at least most of you. Except there's 1700. That peak is showing up at 1650. Why'd you say C double bond O? Super intense. It fell outside of the range. Why? Something else is going on in the structure to cause it to shift.
And you have some bumps in the higher.
Yeah, that's dangerous to apply anything to those. Okay. So yes, that's falling outside of our standard range, but it still matches the shape of our standard IR signal. Make sense? Okay. Questions about IR? Okay. And let's blow some stuff up. Mass spec. Mass spec, we take our sample, okay, we put it into our little injector, and then we've got some massive, powerful, nasty stuff happening in here. Variety of different ways that we can destroy the molecule. One is just an electron beam. We fire electrons of high enough energy at our molecule, and it breaks another electron off the molecule. Okay. So our molecule is now changed. It is missing an electron, which means what happened to its mass? Nothing. What happened to its charge? It's now positively charged. Okay. That molecule being positively charged is going to try to stabilize itself in any way it can. The way it can do that is by ejecting pieces from it. Okay. So it will try to stabilize that positive charge by just breaking sections off, saying, peace out, go over there because I'm a little bit happier if I get rid of you. Okay. The next part is that our sample is then passed through this kind of system, and it's getting sent through a magnet. That's weird. Why are we introducing a magnet? Magnet introduces charges. What if your particle is not charged? It doesn't feel the magnet, and instead, what does it do? Runs right into the magnet and makes farty noises. Every other particle turns. Okay. We now put a nice long gap in between there and our detector. The point of that gap is to do what?
Allow for the certain particles to travel faster.
Allow for the particles to separate from each other based on the speed at which they move. The larger the particle, the slower it moves. So all we have to do now with the detector is just sit here and say, whoops, something hit me. Okay, something else hit me. Oh crap, 50,000 things just hit me. No, nothing hit me. Nothing hit me. Oh, another 5 things hit me. 20 things hit me. So all it's doing is counting at particular time intervals. We can correlate that time back to a mass to charge ratio. Okay? That gets us an idea of how large each of those particles was. Not only how large, but then how many each of those particles hit at an individual time. And so what we end up seeing, don't look at any of that. Oh, shoot. Never mind. Oh, there it is. What? There it is. What we end up seeing is this kind of patterning. We have the intensity, how many times our detector got hit, based on roughly the time, which then gets correlated out to a mass. So your x-axis represents the mass to charge ratio. We have to include charge, because the only things we're allowing to hit the detector are charged. Okay? The abundance, you'll notice one of your peaks will always reach 100% abundance. Well, that's weird. How did that happen? All you're doing is counting. It normalizes the data. Okay? So the whole point is to normalize it out. Whichever one's the biggest gets 100. Everything else is scaled according to that signal. And we see a bunch of lines. Those lines represent how often that piece hit the detector, or something of that mass hit the detector. If we start with a standard molecule, say like 2-methylpentane, and when in pure, that methylpentane, 2-methylpentane, is going to break apart into characteristic pieces. What we can do is analyze those pieces. Okay? So now if we go all the way back through, let's get to the nitty-gritty detail of what we can get out of this. Okay? Electron beam hits, poof, ejects an electron, we end up with this piece. Electron beam hits, poof, where did the electron beam hit? The bond that was holding those together. Okay. Electron beam hit, poof, where did it hit? The bond holding those two pieces together. We end up with different pieces coming out of it. Okay. We then just look at the mass of those pieces, of the charged pieces, to determine our mass spec. Okay. So, a lot of this comes back to this idea of cation and radical stability, because we're forming radicals and we're forming cations. What makes all of these species unstable? Not satisfying the octet. We are short electrons. Okay. So would I expect all of these to be equivalently unstable? Okay. Well, they all don't satisfy the octet. Why would I have a difference in stability between them? Well, maybe there isn't one. How do we figure out if there's a difference between, say, atoms? We could look out and compare. We look out from the center carbon. What's the first thing we encounter? A bond. Ooh, what's in a bond? Electrons. So how many electrons are there? 2. Oh, 6. Oh, okay, let's look at the next one. 2. Okay, well, that was crappy. I didn't find a difference. So what should I do? Move a little bit further out. What do I encounter? Hydrogen. What does hydrogen have? Okay. I won't accept 2 electrons. I will accept 1 electron. Even that's kind of questionable because its 1 electron is shared in the bond, which we already accounted. But let's say it has 1 electron. How much does that one have? That one. So how many electrons are now around that carbon that are potentially different? 3 coming from our hydrogens. What happens when we move to the next one? I go out to hydrogen. There's 1. Hydrogen, there's 1. Carbon. What's the difference between carbon and hydrogen? Carbon has more electrons. How many electrons do we want to say carbon has? Either answer is acceptable on that. So let's go with 4 because I heard that first. So we would have a total of how many electrons around our second molecule? 6 around the first one? 3. How about the next 2? 9 and 12. Are those electrons going to make a difference in the stability of the positive charge? What made the positive charge reactive? It was missing electrons. Which of these has more electrons around our positive charge? The bottom one. What does that mean happens to that carbocation?
Less likely to break.
It is more stable. It is reactive because it is missing electrons. It is less reactive than all the others because it has more electrons around it. Radicals have the exact same principle following behind them. They're just missing one electron as opposed to missing two. So if we're looking at our reactivity, radicals and cations react the same. This goes back to our primary, secondary, tertiary, right? Tertiary means we have 3 carbons. Secondary, 2 carbons. Primary, 1 carbon. What if we have no carbons? Okay. Everybody refers to it as methyl within the scientific community. Go out into the scientific community and tell them wrong. Tell them to call it zeroary because it's more fun. Okay. And we now have a way to establish something about stability. You guys think you get it? Okay, curveball. What are we looking at in this last one? The anions. They have extra electrons. Which of those is more stable? The one with the least extra electrons around it. Which then means our most stable anion is the methyl. All back to following how your electrons either repel or attract in different situations. Okay? While this is important for mass spec, this explains most of the chemistry we'll see at the end of the semester, which is why it's showing up in mass spec and why I'm spending some time talking about it. Okay? The stability of these carbocations is how we get fragmentation patterns in mass spec. Okay, come on. So, what do we get out of mass spec? M plus peak. The peak furthest to the right, but it should also be the tallest peak. That is now the molecular weight of your compound. Using that, you can determine unsaturation once you figure out the formula. How would you figure out a formula? If I give you a mass of 7, that's not the right button. Still not the right button. If I give you a mass of 74, how can you tell me a possible formula? What is this class? Organic. Which studies? Carbon. More than likely, that 74 is including the mass of carbon. So divided by 12. What do we get? 6 in a small change. Okay. So we could go through and say that there were 6 carbons in our compound. But 6 carbons gets us to what mass? 72. Not to 74. How do I count for that last 2 mass? 2 hydrogens. What are the odds I'm going to have a compound of 6 carbons and 2 hydrogens? Not very good. So what does that mean? Take a carbon away and have 5 carbons and 14 hydrogens. How do we do that math? Carbon weighs 12. Could I have 4 carbons? So I heard yeses and nos. Theoretically, yes, I could go drop down to 4 carbons. Why'd you say no? You'd have 26 hydrogens. Could we possibly fit 26 hydrogens around 4 carbons? No, so that formula does not work. If there's other atoms present, we can't be using this same formula system. We have to account for it out of the 74. How can we identify if we have other atoms? IR is the first place. IR will tell you you have oxygen, potentially. Does it tell you how many? No. So if you see a signal show up in your IR that says you have a carbon-oxygen double bond, all you know is there's at least 1. So just run your calculation with 1 oxygen. You would then subtract 16. The next things you can do, look at the molecular weight. If it is odd, nitrogen is present. Okay? This comes because nitrogen has an odd number of potential bond partners. M plus 2. M plus was our molecular ion. If we add 2 to it, we would become 2 units heavier. How would we become 2 units heavier? You add neutrons. Why would this show up? Mass spec looks at mass. Okay? There are some isotopes, bromine and chlorine, that subdivide out into 2 very, very common isotopes. Bromine has 2 common isotopes, one of 79, and one of 81. Relative abundance, 79, 51%, which means 81 is 49%, which means the height of the M+2 signal, if bromine is present, will be the same height as our M+, relatively the same. Chlorine has a similar situation, except it should be 3 to 1, not 1 to 3. Okay? 35 and 37. Last one. Iodine is massive. I might just throw it on there just for the hell of it. If you see a massive molecular weight peak, okay, then iodine is probably there. Okay? Remember, iodine weighs on its own 127. The smallest molecule I could give you would have to be, what is that, 150, 145, okay, as a molecular weight. Right off the top, our guess was 74. Okay? Odds that you see iodine, very, very limited. Yeah.
So nitrogen would never have an M+2? Because
Nitrogen will not have an M+2. Our M+2 only comes in at bromine and chlorine. Only those two.
I had a question that I was looking at that was had an M+2, but it was odd. They were odd.
So what does that mean? You have an M+2 and you have an odd signal.
It would just be bromine or chlorine still, right?
And nitrogen.
But it had an M+2.
Okay? So nitrogen is because it's odd.
Okay.
So it's odd, and you have an M+2, bromine or chlorine is also present. So multiple things can happen in the same spectrum.
So what happens if you have both bromine and chlorine present?
It messes with your whole patterning at the end. Yeah, you don't want to look at that. So, fragmentation patterns. Why does it do that? What is going on here? I have to go back twice to get the figure out. Your multiples of 12 we already talked about. So our M plus peak here, we look to the peak furthest to the right. Tallest peak there, 86. That is our M plus. Do we have a peak plus 2? No. So no bromine or chlorine. Can we have iodine? No, because iodine hits us minimally up at the 127. So we can't have iodine. Okay? We could then analyze to get our molecular formula, and we'd get a molecular formula that would match that structure. You'll notice that I say nothing about the peak at 71, 57, or 43. Why not? Those are harder to analyze. That is how the structure blew apart into individual pieces. Could you still analyze those? Yes. And if you become good at developing formulas for 86, try and develop what a formula could be for 71, for 57, and 43. Add to that information that the reason the 43 is so intense is because that piece is incredibly stable. So determine how many carbons could theoretically go into that and how you could make that a very stable structure. You'll find that that 43 corresponds to that piece. Why? The carbocation would be on that secondary carbon. That is the most stable place that you could put the positive charge. Okay? So the molecule, as soon as we hit it with an electron, breaks apart and it generates that piece. We see that piece at 43. That's what's happening. Do you need to know that? No. What do you need to know? That. Do that. Okay. Yes?
Recombination is really an issue with this.
We do not worry about recombination.
Okay.
After that, we've got NMR, no mass spec. So NMR, it's kind of hard to go through and deal with this because we can get into some hardcore theory on what's happening. Okay? We are looking at the spin of a nucleus. So electrons have spin, so do nuclei. Okay? If you have charge that's moving, there is a spin state associated with it. So our nuclei will generate a magnetic current because it is moving and it is charged. That magnetic current we can detect with the instrument. Okay? Just being able to detect it isn't quite good enough. What we want to be able to do is tweak it to see how that magnetic current is different from magnetic current in other locations in our molecule. So what we end up doing is taking our sample and we drop it into a magnet. Okay? What's going to happen is all of our nuclei are going to align with the magnetic field. We then hit it with radio frequencies. Radio frequencies disturb the nuclear rotations. So we cause our nuclei to then spin off axis, and we can or monitor the time it takes for them to get back to the ground state, being aligned with the magnetic field. Okay. That's the bare bones of what's happening. Okay.
And the rotation speed is a set figure, or?
Our rotation has two possible rotations. Well, there's tons of possible rotations corresponding to different atoms within it, okay, or different nuclei. So that's the big thing, is we will scale off of certain nuclei. So we're going to set our magnetic strength and our radio frequencies to pair with a certain type of nucleus. Okay. The two common ones, carbon and hydrogen. Hydrogen is used much more frequently, and the reason why is that the hydrogen nucleus, 99% of hydrogen is protium, is sensitive to the magnetic field. Deuterium, another hydrogen-type nucleus, is not sensitive to the magnetic field. Okay? So the balance of protons and neutrons causes it to be detectable within our magnetic field or not. So hydrogen is super common because 99% of all hydrogen we can see with the instrument. Carbon we also end up using. The issue with carbon, though, is carbon-12 is not detectable via our instrument. So what do we have to use? We have to use one of the other isotopes of carbon. Okay? We end up using carbon-13. Carbon-13 makes up 2%, something like that, of our standard carbon isolations. So if we wanted to see a carbon spectrum, we could go through and enrich our synthesis with all carbon-13. That would make detecting it very, very easy. Okay? Or what we do, run the spectrum or the spectrometer for a longer period of time. It'll still only detect that 2%, but if you start detecting it for long enough, you can build up enough signal to noise that you can see a signal. That's what we end up doing for our carbon NMR. Are other nuclei possible? Yes. Okay, but it is relatively limited. Carbon and hydrogen just happen to be the most common. The next part that we need to consider are electrons, while not part of the nucleus, are also moving as charged species. That motion of electric current then does what to the ability of the nucleus to see the external magnet? Changes it. So our electrons can hide the nuclei, make them difficult to see. Which then means I can say something about the local environment. The electrons around that atom will cause the signal to show up differently because I have to give it different amounts of power to get it to respond to the magnetic field or the radio frequencies. All right? So your spectrometer, nasty big magnet, you drop your sample in, you've got your RF transmitter, so firing off your radio waves. You notice that time, your magnetic field fluctuates, okay? And then you put that out to a printer that monitors the magnetic field, and we just see when we see peaks. Okay? Kind of as simple as that. This happens to be an 850 megahertz magnet. To give you an idea of scale, that is 2 stories. Okay? This is a really, really big NMR, which is one of the reasons why we don't have them. Okay? A standard kind of IR instrument is 300 megahertz. It's about that tall, okay? And it's probably that big around. Okay? They are pretty freaking massive. If you go to NMR, or go to NMR, that university nearby, ASU has an awesome NMR lab, and the instructor or the organizer of the NMR facility is actually a really good guy that encourages undergraduate research. So if you're interested in that, you can talk to me after class and I'll let you know what's going on with that. Okay? But you end up playing around with these magnets and spectroscopy. Some experimental considerations. Okay? we run into issues with standards. Okay? When we're looking at our NMR, we're saying our signal is either more or less shielded, meaning it has more or less electrons. More or less electrons than what? We don't know, which means when we look at our spectra, we just see a bunch of random peaks with no way to interpret where those peaks are relative to each other. So what do we have to do? We have to standardize it. And we standardize that by adding another species. The standards, or the most common standard used is TMS. Okay? Tetramethylsilane is our internal standard. So in most spectra, you will see a little peak at 0. That 0 is TMS. That's how we determine our standard. Okay? So where should our organic protons absorb? Okay? Well, this is now referencing where we're at on our curve. It's typically referred to as downfield. So if we looked at a spectra and we established a 0, downfield is over here. Then we also have upfield the other direction. Most organic spectra, our signals show up downfield of TMS. Hence we end up seeing our lines go from 0 all the way out to 14 on the left, in kind of the reverse order that we would expect a number line to go. Okay? The sample must tumble and move. It's an interesting question. Why does that have to happen? What is the difference between these structures? They're the same. They're the same because they rotate bonds. What if they can't move? Technically, they're not different. They'd be isomers of each other. They aren't identical anymore. If we're looking at NMR, we're trying to decide the relationship between the hydrogens in these molecules. If our molecule does not freely tumble and move, it sees two different types of hydrogens. That's a problem. Okay? It is one that has since been worked out, but under most circumstances, we need to have our molecules freely tumble and move. Okay? Which means we can only test liquids. Liquids are the only thing that can freely tumble and move. The solid wouldn't freely tumble and move. How could we get a solid to act like a liquid? Dissolve it into a solution. We could try and melt it, but that's going to get too high a heat. That's going to be a pain in the butt. Okay? So we'll dissolve it in another compound. What's the problem of adding another compound? Most other compounds have hydrogen, which means when we look at our spectra, we'd see a massive signal for our solvent and nothing for our compound. So what do we have to do? Whatever solvent we use had better not have hydrogen. But hydrogen's everywhere. How do we get rid of hydrogen? I already mentioned the answer earlier. Deuterium. Replace all of your hydrogens with deuterium. Okay? So you'll typically see chloroform and dimethyl sulfoxide as your standard solvents. Both of those solvents have hydrogen. We can't have hydrogen in our signal, so they become deuterated. And we get CdCl3 for our chloroform, or D6-DMSO. Why D6? There are 6 hydrogens in dimethyl sulfoxide. Okay? Even with that, you will still typically see a signal for those. Why do you see a signal? It's known as a purification issue. What are the odds you'll be able to get all of the hydrogen swapped out? Not the greatest. So you end up seeing some of that signal show up. Let's say you were even able to purify it super cleanly. What happens the instant you open the container? There's water in the air. What happens? Water supplies hydrogen, and you get an exchange of hydrogen for deuterium in the free environment, and hydrogen shows up anyway. Okay? So the idea is to minimize our signal as much as possible for our solvent, but that's about the best we can do. Okay? So this is the big summary slide on what happens with NMR. Okay? And this is what we'll end with and pick up with on Monday. Okay? And that means also that you should be ready to kind of talk about any questions that you might have on Monday because the exam is Wednesday. Okay? when we're looking at our things to get from an NMR, there are 4 things to evaluate. The number of signals, the chemical shift, where it shows up on the axis, the integration, how tall the peak is, and multiplicity. How many times does our signal split or break apart? Okay. When we look at levels of difficulty, the number of signals is relatively easy to do. You just count the groups of peaks and then do an interpretation. Well, what would your interpretation be if you see 4 groups of peaks? 4 unique hydrogens or 4 unique carbons. We get information about the numbers, the relative numbers of our hydrogens and carbons in an individual structure. Okay? Chemical shift is now where it shows up on that x-axis. Well, that x-axis is all telling us about how many electrons are around it, okay? Which is telling us something about the chemical environment that that atom is located in. So in our chemical shift, it gets us the rough idea of what's near that hydrogen or carbon, meaning what is it bonded to? The integration is the area underneath the curve. How tall is the peak? The taller the peak, the larger the area. Well, the only reason it gets taller is because there's more things showing up at that chemical shift. Okay? So it's giving us more hydrogens. The biggest issue to realize with this is it only gives you the ratio. And depending on how nice we are about the information and how it's supplied, that may be the reduced ratio, or it may be the correct ratio of how many hydrogens are actually present. Okay? You'll notice it does not reference carbon. Okay? And that's because carbon signal can get influenced by hydrogens, which messes with the interpretation. Okay? So we have to do other kind of experimental considerations instead of looking at integration. The last one is multiplicity, also known as splitting. It's the number of different neighbors, or it corresponds to the number of different neighbors. We look at an individual signal, it will break apart into a different amount of peaks. If we look at the difficulties again, counting the number of signals, easy. Chemical shift, easy. You do the chemical shift just like you did IR. Is there a bond present? I see a signal. Okay? Integration, a little bit harder because you have to watch out for that ratio, but it gets us an idea of how many hydrogens are present. Multiplicity and splitting, stupidly difficult. Unfortunately, everybody jumps to multiplicity and splitting first because it has the most information in it. Don't do that. Do the other ones first, because the other ones can get you to the final answer. Once you have the answer, it's a lot easier to work backwards to figure out what you should have seen somewhere else. Okay? So process through the first 3. I fully expect you to be experts at the first 3, IR, barely mass spec, and UV Viz for the next exam. This last one, you will see questions there. If you're good at it and you've practiced, you can answer those questions. If you haven't, accept them as a loss. Don't worry about it. Okay? Read up on that.